Okay, so question 50, sub-question A. Which oxygen has the greater electron density? So this question, like a lot of these other questions, is very much dependent on you being able to draw effective resonance forms. So the first thing you have to do is recognize that, okay, this ester, it's going to be almost be impossible to tell the difference between electron density on this oxygen down below and the oxygen up above just by looking at it. Very, very difficult. One way you can get an intuition about what oxygen has the greater electron density is to draw resonance forms. So we'll get a little bit of an insight into partial positives and partial negatives, because obviously both of these oxygens are neutral the way they're drawn, but one of them will have a little bit more electron density surrounding them than the other. Okay. So first things first, let's go ahead and play around with lone pairs. One way you could potentially push electrons around for this guy would be, well, an incorrect way would be to take this lone pair and try to come down like this. If you did that, then you would get the following resonance form with an oxygen with a triple bond, which first off looks really freaky. Second of all, you have a carbon with 1, 2, 3, 4, 5 bonds to it. So for several reasons, this is an invalid resonance form. The first is that you have this kind of um, Texas carbon configuration, and then also charges are all wonky. Anyway, for this, don't try to do that. So this first electron push is totally wrong for multiple reasons. Texas carbon, we're not really breaking the octet rule for this oxygen, but 6 minus 5, 4, 3, 2, 1. Positive charge on an oxygen is always messed up. Well, not always, but it always looks a little weird. Especially if this carbon would have a negative, which it would, if we weren't breaking the octet rule, which we are. Okay, so that's no good. So let's go ahead and erase that electron push. Let's erase that. So we can't push these electrons down. We can't really push these electrons in the pi bond down this way either. This is going to be bad news. So if we try to do that, this is what you would get. So in this case, you would have 1, 2, 3, 4, oxygen, oxygen, and we'd have 1, 2 lone pairs here. So overall, still this oxygen would not be neutral, it would be positively charged. Double positively charged actually, so 1, 6, 5, 4, 3, 2, 5, 4, 3, 2, 1, yeah, positively charged. So that's no good. Then the other thing wrong about that is this oxygen in the middle has 1, 2, 3, 4, 5, 6, 7. It has a formal negative, but it's also breaking the octet rule. So 2, 4, 6, 8, 10 electrons surrounding it. Okay, so that's no good. So neither one of these is going to be right. So let's go ahead and draw that guy as right out. This gives a frowny face too. So the other possibility is if we erased that yellow arrow, get rid of this guy. And so what if we did this possibility where we use the electrons on the rightmost oxygen? If we did that, we can push electrons onto this carbon-carbon bond. And if we do this, we have to try to break a bond because we're making a bond, breaking a bond. So if we broke a bond, this seems to work okay. So we can draw this resonance form coming down here and write what we would get from that. In this case, we would get an oxygen with 1, 2, 3 lone pairs, and we would get a double bond between the oxygen and the carbon, and this oxygen would have a lone pair still. So this oxygen would be 6, 5, 4, 3, 2, 1, positively charged. This oxygen up above is negatively charged. Okay, so there's absolutely nothing wrong with this electron push at all, and even though this oxygen is positively charged, that looks a little funky. It's balanced out by this other oxygen with a negative charge, and neither one of them are breaking the octet rule, which is fantastic. Okay, so in this case, this actually helps us. So first off, actually, this is totally valid way to draw a resonance form, and this also gives us a little bit of a hint and intuition about which oxygen has the greater electron density. Because remember, neither one of these resonance forms, this guy down below or this guy up above, is real. They're both partial contributors to reality. So this structure of this ester doesn't actually exist. and neither does this one below. The reality is actually reflected by the merging of these two concepts into one big concept that we can't actually represent very easily on paper. Okay, so this is actually partially real. So it gives us a little bit of intuition or information about where that negative charge would be. So in this case, this top oxygen has a negative charge, bottom oxygen has a positive charge. So because of that, this top oxygen is going to have greater electron density. Okay, so greater density because we have a formal negative, and this bottom oxygen is going to have lesser density. Okay, so overall, not too difficult of a problem. You just have to remember how to draw resonance, and you have to be able to accept that resonance can actually tell you a bit about where electron density lies. Is it a perfect system? No, it's completely imperfect, but for first impressions, it's pretty good. Okay, all right, next question.